One says that relative time position, so I talk about your yesterday or my future. This is one view. And the other view is the view that really there is no time.
Today we have something special. The man, the myth, the legend, Professor Lee Smolin. Professor Smolin's work in theoretical physics spans several decades, focusing on quantum gravity, the foundations of quantum mechanics, and cosmology. He was also instrumental, along with Ashtekar and Rovelli, in the development of something called loop quantum gravity, which is a competing theory to string theory, one that attempts to make consonant general relativity and quantum theory. I've spoken to both Ashtekar and Rovelli on the podcast before, and the links to those in-depth 3-hour discussions are in the description. Lee Smolin is exalted not only for his contributions to theoretical physics, but to his contributions to the philosophy of physics. His research in quantum cosmology and the role of time in physics led to the proposal that the laws of physics aren't fixed over time, but rather that they evolve. One variation of this is that whenever there's a black hole, there's a new universe that's birthed, and the physics of this embryonic universe has slightly varied laws. Lee is also a time realist. Now, this sounds like a strange proposition because colloquially we think, hey, well, time is obviously real. But the difficulty is, well, what do we mean by real? And then secondly, how do we explain that mathematical equations are timeless? This latter view is also known as Platonism, and Lee is not a Platonist, at least not anymore. Lee has also been diagnosed with Parkinson's. This is a neurological disorder that he once hid from others during the early stages, but he's now decidedly open about it. In fact, Lee valiantly wanted it on display without blandishments in order to bring attention to the issues of Parkinson's. This is one of the reasons why the audio was tough to capture at different points. I was filming this alone with limited resources. Usually I'd set the camera down static, but Parkinson's makes it such that you must move about. Thus I used a handheld camera and I had to balance both the framing and the audio and interviewing itself. Every word of this interview, just like every other Theories of Everything podcast, is meticulously transcribed, so you can enable the captions on YouTube. Every podcast is translated in over 20 languages. You can also visit kurtjaimungal.org for transcripts. Speaking of which, my name is Kurt Jaimungal, and this is a podcast called Theories of Everything, where we explore, generally from a theoretical physics perspective or a mathematical one, what are the constitutive laws of nature, what is reality, as well as, well, what is consciousness, and do the laws of nature have some relationship to it? Also, what is free will? More, we've been delving into AI, and soon coming up is a set of lectures from MindFest, such as some from Scott Aronson, Sarah Walker, and Stuart Hameroff. Next week, I'm going to be publishing a colossal, rigorous, exhaustive video on the mathematics of string theory. There's also going to be a subsection inside covering loop quantum gravity, so subscribe to get notified, as there are new videos every day on this channel. Now enjoy this interview with the man, the myth, the legend, Lee Smolin. I'll start off with a joke.
Okay.
Stephen Wright, a comedian, said, "Someone asked me, 'Can you tell me what time it is?' And I said, 'Yes, but not now.' So what is your idea of the thick present?"
A good joke involving time. Now, the thick present is an idea of some philosophers, I don't remember who right now, that time has an extension, that so that there can be two events which are at the same time, but one is to the future of the other way around. So as a technical idea, it's clear what it is. It's to be subtle, though. Does it violate relativity? And I think it challenges relativity.
What's the difference between contradicting relativity and challenging it?
Understanding something and not quite understanding it yet.
So there's something that you have invented called Doubly special relativistic theory.
With some friends, yes.
Yeah. What is that, and does that violate Lorentz?
It extends Lorentz invariance. The idea of doubly special relativity is that, well, let's go back to special relativity. In special relativity, we have one scale, one velocity, which is invariant. So when we travel, if we're traveling, you're going that way, I'm going this way. We have a relativity, Galilean relativity, whereby our length and time measurements change relative to each other. But in doubly special relativity, we impose the constraint that not only is the speed of light fixed under those transformations between frames, but so is an energy. So that if we measure a energy of some particle, we can transfer between your measurements and mine, and the transformation will be more complicated in such a way that there are two length scales, or one velocity and one energy, which remain invariant.
So is another way of saying that there's a universal cosmic speed limit, which all observers agree on, but then also a universal cosmic limit to the length? So the Planck length is somehow also fundamental?
Yes, although I'm trying to keep H bar in the game. So I'm trying to, I want to pick whether it's an energy that's invariant or a length that's invariant. I don't want to assume that H bar equals 1. And what you decide is that what's invariant is the ratio of what we usually call the Planck energy to what we usually call the Planck length.
Why is it that you don't want to set H bar to equal 1? Is there something that you feel like is lost?
Yes, because if we want to have a theory which explains H bar, it can't be one in which H bar equals 1.
Uh-huh. So what led you and your collaborators to develop this?
Sabine Hassenfelder, to be short. We had a previous theory which was doubly special relativity, and we didn't understand it completely. And Sabina saw that there would have to be non-locality in some field theory if that theory was going to encompass doubly special relativity. And so we then, and this was 4 of us, we were working together a couple of times a year at Linear, and we realized more or less simultaneously that the way to answer Sabina was to let simultaneity be relative and also let locality be relative. So whether some interaction took place locally or non-locally was dependent on whether you were close to the system being observed or far from it.
Mm-hmm. So what did Sabine say to the concept that locality itself is a relative concept?
She didn't like it, and we continued to have disagreements, and I think she continues to disagree with us.
And her disagreements are
that you can have a theory. Now we call the theory, with these amendments, we call it relative locality, because that's a more precise description.
Okay. Speaking of what's relative, there's something called A and B series of time.
Yes, I never remember which is which, but in one of them, the one says that relative time position. So I talk about your yesterday, or my future, or the dog's past, and those are relative to the dog at some moment. The past of the dog is not the same as whole future at another time. And this is one view that that's okay. And the other view is the view that really there is no time, so that there is only, I think I'm saying it backwards. In the one view, let's call it the A view, although I'm not sure that it is what it's.
Sure.
You can be an observer to the future of another observer. And we allow that is, we allow ourselves in the theory to discuss relative time as realistic, real things, but relative to an observer, if that makes sense.
And is this related to your thick time or no?
It needs thick time to make it consistent.
Have you heard of Nicholas Gissens or Nicholas Gissens?
Oh, sure.
Well, what is his concept of thick time, and is it different?
I don't think so, but I haven't studied it.
Okay. So explain to me why thick time needs, or why A or the B series needs thick time.
Can we come back to that?
Sure. Something that the viewers may notice by now, and I've already mentioned it in the introduction, is the movement. And you mentioned that you don't want to hide any of this.
Well, it would be hard to.
Yeah. So can you explain?
What you're seeing is an overcompensation for Parkinson coming from taking a bit too much dopamine, which is, in the context of being interviewed, a good thing to do.
Why?
Because the other setting, it's a very quick transition. And I think it is a phase transition. By the way, I'm doing some work on the brain and the regions of the brain which are relevant. It seems to be that there is a phase where things seize up in the control of the brain,
Yeah.
and a phase where things go uncontrollably nuts.
Okay.
And you want to be in a kind of critical state between them.
Yes.
And that's what the dopamine allows you to reach.
Yeah. And so right now you're in the critical phase, or you're pushed off to one of those directions?
I'm way overcompensated.
Oh, but does that mean that with time it will get better, or
Yes.
with time it gets okay? With time throughout this day, I mean.
It's coming right up.
Oh, okay.
And you'll see it happen because the critical phase, as in most physical systems that have a critical phase, is a cause of critical vibrations. So you'll see, I'm making it happen, but you'll see half an hour from now my things going critical with critical scaling, and then it'll be over.
Does it just affect your physical body, or does
It
your
affects everything.
okay? How does your mental state or your state of consciousness affect it?
It makes me. I don't have much of an executive function when it's on strong.
Uh-huh.
So that's the worst thing. Is I can overreact.
Yeah. So why don't you talk about how you studying physics, well, it's more like researching physics has been impacted. Your collaborations even.
It's more irregular. That is, working with my collaborators, I'm on more, and we use the words on and off. So, but I don't know. You have to ask them. Although I don't know if I want to know the answer. I'm glad to have still collaborated.
When we talked a couple of years ago on the phone briefly. I don't know if you recall, but I was asking if you had taken a look at geometric unity because I was going to be interviewing you at that time, and I was giving an overview of some of the questions. And you mentioned Eric is a dear friend.
Yes, he has to be. If he's not your dear friend, he's not going to be your friend.
Yeah. Okay, so can you please talk to that? And then also geometric unity.
Eric is, well, his strength as a researcher is certainly his commitment, and he's extremely smart, extremely quick, and he can go at something for years and years and years. And that's very important if you're trying to do original work in physics or anything else, I would think.
Is this quality of going forward on a single idea or a single theme for years rare?
Yes.
So it seems like for me, when I was reading your work, and by the way, you don't know this, but so my background's in filmmaking, like math and physics, and then I did a film.
Okay, what was the film?
Film is a dramedy, so comma dramedy, called I'm Okay. It's a heavily Toronto-based film.
Oh, so I may know people in it.
Yeah.
Because I know a lot of film people.
Yeah, so when I was filming it, and I had the cinematographer in my car and the sound recordist in the car, we would be listening to your book.
Oh, wow.
Yeah, one or two of them during the filming of it. Anyhow, that was a fun experience because they would ask me, what's a Causality manifold? They wouldn't pronounce it like that, but they would say, so what is that? And why does that have anything to do with background independence? And why does background independence matter? Why does gravity have anything to do with curvature? Curvature of what? Space? No, not curvature of space. Curvature of space-time, which is different than space. Anyhow, this interview itself, just meeting you, it's a dream. I would be listening to you in the car. I had no idea that I could ever not only see you in person, but shake your hand and speak to you like this. So thank you.
You're welcome, but that's extraordinary to me because I just live here, and I don't feel very well. The Parkinson's has a way of leveling things.
Mm-hmm.
I would say everything is now in question. Every interview, every talk every paper is a experience sort of on the edge.
Meaning that you don't.
I don't rest on reputation. I can't. But the work that I'm working on now is my favorite work. I'm very impressed with it, which is a funny thing to say, that you're impressed with your own work. But
And that work is, why don't we just briefly outline it now? We can come back to it later.
well, that's just 10 years ago, what we're talking about.
The work that you're working on now is what?
Is, well, why not? I'll tell you before it's in published paper. But what I've been working on, broadly speaking, is extending the notions of time as real and, well, first I'm a realist, so let's get that out of the way.
Okay.
I'm not interested in physics, which is, there is realistic people and there are people who make physics too
Subjective?
almost subjective.
Like Bayesian?
Yes. But Bayesian is the mathematical realization of this idea.
Okay. So you're not a Bayesian.
I'm certainly not a Bayesian. I'm a good old-fashioned realist. I believe that there is a way that the world is, and I'm interested in knowing what that is.
Realism to most people means something's external and objective. Is that what you mean?
Yes. But at the same time, I believe that the world has to be understood in a language of what observers see. But it's very important to me, that there are many observers. And so Einstein allows you to just have an observer and another observer and talk about their relations between what they see. Einstein is a realist, but he is using the methods of this thing that we can't understand. We can't remember the name of.
So it sounds like there are objective and subjective elements. And what you're saying is that there are some people who believe there are only subjective elements, and you're not one of those.
No, I'm saying that we can talk about and record and work with other people's observations as well as your own observations. So, and they're all real to you. And it's just a word, which is it's what Lucian always calls himself, Lucian Hardy.
Lucian Hardy?
Lucian Hardy.
Yeah. Okay. What does real mean in this instance? Because you said it was real to you, which to me sounds subjective.
Yes, that's unfortunate. Real means that I'm interested in what makes up the world and what the world is. I believe that if you took me out of the world, it would still be the same. But you still can make interesting transformations between what one observer will see and describe and what another observer will see and describe.
I see.
Sabina's I'm a recent strong fan of Sabina.
Okay.
Sabrina. And one of the things that she likes to say is that every problem in physics is a translation problem. Because the argument between string people and loop people, which unbelievably we still have going on, is a translation problem for her.
What does that mean?
They're both right in different regimes. And
yeah, I recall reading one of your books. Forgive me that I don't know the name, because there are several. And in one of them, you mentioned that you believe loop quantum gravity to be a subset of string theory. Or no, you said there was a duality between them.
And yes, but I know that's way too simplified.
Okay. Yeah, and you used the word duality, that there is a duality between them. And I don't know if you used that word poetically or if you meant that mathematically there's duality.
There are theories which are dual to each other. And for example, one of them is you can take electromagnetism and you can look at its phase with the magnetic field frozen. That means that magnetic field expresses itself by making magnetic field lines discrete. And so then you have a phase of electromagnetism where magnetic field lines are discrete. You have a phase where neither field lines are discrete. That's the usual behavior of electromagnetic fields. And then you can go into a dual to the magnetic field lines frozen, to where you can go into dual of the phase where the magnetic field lines are frozen to a phase where the electric field lines are frozen. And that's what in the phase where electric field lines are frozen, you have confinement.
Mm-hmm.
And the confinement is represented by the frozen electric field lines, which means that there's a cost in energy per length of the electric field line. And that's why the quarks behave in a way which is confined.
Yes.
And we believe that that's the way that non-abelian gauge fields behave when they represent the gravitational field.
So that would be an example of a
Loop
duality.
quantum gravity.
Okay.
Being dual to a field theory of gravity.
Uh-huh.
Which is described by general relativity.
Is this another way of saying that there's a translation issue, that they describe different regimes, or this is a different phenomena?
I don't know. But it's a way of explaining what happens in loop quantum gravity.
Ed Witten was once asked, recently actually, in the past 5 years, what about other approaches to quantum gravity, other than string theory? And he said, what other approaches?
Right, of course he would.
And then they listed some like causal sets or loop quantum gravity. And then he said, well, the reason why string theory is supreme is because the mathematics of those are described in string theory, or tend to be more and more. String theory tends to gobble up, whereas those don't tend to gobble string theory. So he said, if there's something to loop quantum gravity, I'm sure we'll discover it in string theory as well.
They already have a long time ago.
Oh, can you explain that? And what do you make of that statement overall? I was paraphrasing, so please don't quote me on that.
Oh, that's okay. I mean, what am I supposed to hire? His father was a good friend of my mother's. And
Lewis Witten.
Lewis Witten, yes. And I think, I don't know, here's something I realized recently. Ed used to give me advice. Edward used to give me advice. And I used to misunderstand it because I was too oversensitive to being criticized, and especially by him. For example, he would come to me and tell me, when I was a graduate student, he would say, you really ought to have a research program and develop it. And I said, but Edward, I have a research program, but he never was interested in mine. That's the way it felt. Well, not recently, but maybe 20 years ago, I was for a day at the Institute. I gave a talk and so forth. And he came over to me and he said, I have some advice for you. And I said, sure, what? And he said, you're really smarter than you look. And for people to become convinced of how smart you are, you should get out of quantum gravity for a while and work on condensed matter theory. Because there are a lot of people who are working on interesting problems, and people will get to see how smart you are. Now, I heard that as criticism.
Okay.
But I think he was actually trying to give me what would have been, if I couldn't have taken it because I'm interested in condensed matter theory. I'm interested in applying ideas from condensed matter theory to loop quantum gravity, and that would be one way to explain to Edward what we're doing. But I took it as a strong criticism, whereas I'm sure he meant it kindly as advice.
Mm-hmm.
And so we all evolve. Anyway, I know what Edward is trying to say. I think the reverse is true. And I think there are a lot of results related to loop quantum gravity, mathematical results, that if he took the time to learn, he would see what their purpose was. in string theory. And I don't like to talk about string theory and quantum gravity. I would rather talk about background independent and background dependent.
Sure.
Because I'm sure that they're the same theory.
There are background independent approaches to string theory, though.
I don't know any that work with it. But please, show me one.
There are some talks that I saw, and I can send you over email. Recently, in the past 2 years, I'm sure they're of limited applicability, like it's just for type 2B.
Right. If it's ADS-CFT, it's hard for me to be interested.
Mm-hmm.
Because that has a background on it.
Yes.
By definition. And it doesn't allow me to ask the questions that I want to ask.
So Feynman was extremely concerned with appearing intellectual or appearing smart. And one of he talks about this, he likes to trick people into them thinking that he's brighter than he is by memorizing large sums or cracking safes and so on. And Gell-Mann, I think, criticized him for this, said, Feynman, you focus on the marketing of Feynman and not the physics. Like, focus more on the physics. As you age, insecurities tend to dissipate. Maybe other ones creep up, I don't know.
Yeah, they certainly do in my case.
Yeah. What were your insecurities when you were younger? And
well, they mostly relate to women.
Yeah, as they do. Right. Yeah. You know Jonathan Oppenheim?
Sure.
What do you make of his stochastic gravity approach?
I like some of it, but I don't believe if there's a part of it, now maybe he's giving this up, but there's a part of it where he says that gravity is classical. And although I don't believe that gravity is quantum mechanical, I don't believe that gravity is classical either.
You believe it's a third option?
Yes, the third option is that space doesn't exist. Time exists and is fundamental. And space and space-time emerge from the fundamental world, which is basically a fancy version of causal sets. And we can show how our fancy version of causal sets allows space-time to emerge in a way that lets there be, in the emergent level, something like general relativity, but only at the emergent level.
Sometimes when Edward Witten is giving some introductory talks, and when I say introductory, I mean to graduate students or upper undergrads, he starts off by saying, like, let's study this toy model where there's only time, so just 1D system. And let's look at the action of that, and then we'll find that particles emerge from
space in one dimension of time.
No, just 1D, just time.
Right.
Just time. Ricci curvature is just a scalar. All you have is just one extra degree of freedom. So are you saying, hey, Edward, you thought you were studying a toy model? That's actually the universe. There's no toys in that.
Well, right. The problem is that his quoting is continuous. It has a continuous metric.
Whatever gives rise to the continuum, whether it is a continuum indeed or it's something else, you can always still say it's approximated by a continuum. So why does the no?
Okay. The approximating by a continuum is a very strong constraint on this reset. If you have a continuum which approximates some discrete set, that discrete set, well, think about how many dimensions we're talking about to describe the space. If there's enormous constraints on the continuum space, let's think about the other way. If it gives an approximation to a discrete set, and so it's very hard to get for example, a theorem of some mathematician who works with Raphael Sorkin. They prove a theorem that a generic causal set is embedded in 3 dimensions. There are 3 elements in the causal order.
Okay.
So that's very non-generic. So in other words, a generic causal set will not approximate any causal order
Uh-huh.
of low dimension.
Yeah. What is the relationship between causal dynamic triangulation or causal set theory and loop quantum gravity, other than them being discrete?
Well, should we talk about the Hamiltonian version first and then the Lorentzian version? Right, so the Hamiltonian version is the quantization of general relativity treated as a gauge theory, where the configuration variables are the left-handed part of the space-time connection. And you can write general relativity in such a form that is where there's a way to take general relativity and let the degrees of freedom of the metric and the gauge field be independent. So you start with that version of the theory. So there are the 10 degrees of freedom of the connection. And then there are the 16 degrees of freedom. I'm sorry, this is the other way around. There are 10 degrees of freedom of the metric and 16 degrees of freedom of the connection. And you can let all of them be free. And then the equations that restrict them to only metric dependence, so that the connection degrees of freedom are functions of the 10 metric degrees of freedom, become field equations. Okay, so that's a well-known modification or slight extension of Einstein's version of general relativity. You can go one step further and reduce the degrees of freedom of half the connection to the other half of the degrees of freedom of the connection. In other words, that the theory I was at a moment ago has degrees of freedom of the corresponding to the metric, the degrees of freedom corresponding to half the connection, and no other degrees of freedom, because the other half of the connection are just reduced to functions of degrees of freedom of the first half of the connection. And that's called a chiral version of general relativity. Okay. And you can study that as a classical theory, and say Spansky and Ted Newman were people who did that. And then I noticed that in the Hamiltonian version of general relativity, you can do the same. And remarkably, very remarkably, although I don't think anybody put it this way, you could reduce the degrees of freedom. You could make the action cubic in the Hamiltonian language. So we're used to writing the first order action of general relativity as a function of 3-dimensional metric degrees of freedom and 4-dimensional connection degrees of freedom. And then you solve the field equations and you get just the usual Einstein's equations. Yes. But if you take the chiral version of the theory, where there are no right-handed connection degrees of freedom, there are only left-handed connection degrees of freedom, and to begin with, the metric degrees of freedom, you only need a cubic action, an action which is purely cubic in the field. Whereas in all the other forms of general relativity, you need an infinite number of degrees of freedom. Okay. So this is one of these things that everybody should know about the quantum gravity. Yeah. Are there other mistakes or misapprehensions that people have about loop quantum gravity who don't study it? Sure. Or many. But that's the most important. Loop quantum gravity is not a proposal in the new theory of gravity. It's just a way of studying gauge fields, which are diffeomorphism. So Wolfram's physics project, I believe that's what he calls it. What do you make of it? Have you taken a look into it? Yeah, I think it's interesting, but it's not focused enough on things like what we were just saying. I mean, I would encourage him. I think he should work more in the direction he's working.
You think it's misguided, or you think it's just incomplete, or it's too general?
Well, I haven't looked at it in enough detail to criticize it.
Sure.
But if I were in his position, I would study more chiral versions of the beard.
Okay. And that's just because our world is chiral?
That's enough of a reason. We want to understand why our world is chiral.
It's not enough to have some anthropic reason where the world could be symmetric, chirally symmetric, but there's another version of the world that is left-handed, and there's actually another version of the world that's right-handed. We just happen to live in the left one. So it's okay if he's studying symmetric versions, because somehow through some anthropic argument you can get to a chiral version. That's not sufficient.
No, I don't think it's sufficient. And I don't know why the world is chiral, but I think it's very non-trivial.
What about Peter Woit's Euclidean twistor unification?
I think it's interesting, but I haven't really studied.
Okay. He has a new paper called Space-Time is Right-Handed.
Yes, I've seen it, but I haven't studied it. I have a little less energy than I used to.
Yes.
So I'm studying things, I'm working on things that I think are important to the ideas I want to develop. And I apologize if anybody objects to that.
Almost invariably, when I ask someone about someone else's theory, they're unaware of the theory, or they just haven't had enough time to go into it in detail. So you're not alone. When we talked about, let me just see here. Yes. So we talked off air about this question. Look, if we can have a thick present, a thick time, can you have a thick spatial extent? What does that mean?
I don't know what it would mean. Let's come back to that.
Sure.
Let's just think about that.
Yeah. In relativity, there's no preferred now moment.
Yes, but there must be.
Okay. Would there be a preferred now moment for people who are close by to one another? So that is, in some bubble, there is some shared moment of, there is actually a moment of now. There is some notion of simultaneity.
But it's very important that time is one dimension.
It's important that time is one-dimensional. Now, have you encountered, so other than bars, have you encountered many theories of more than one time dimension?
No. I have encountered a few.
Yeah. Geometric unity has multiple time dimensions. Have you had a chance to go into it, or just informal conversations with Eric about it?
I've hardly seen Eric in these years. And then he's involved in these political, whatever you call them.
Mm-hmm. And so you don't like that? You'd like to stay out of politics?
I think I'm happy to join into discussing those political things, but I don't have anything else to say.
Yeah. And Julian Barber's view of time compares to yours how?
Beautiful. I mean, Julian was my mentor in thinking about time. Very strongly my mentor. And I worked with him for years. And for example, the idea of variety, which is an important part of our present program, came from working with Julian.
Like an algebraic variety?
No, like supposing I have a graph embedded in, or not embedded, just in some space. And I want to know, I need a definition of complexity for something. One way to give a definition of complexity is to think about what the universe looks like from one point, from one observer. So that's called the view of the rest of the universe by one observer. And you can define that in several different ways. You can you can imagine that we take the sphere of the world around us with all the light rays coming in from different directions. And then we can define a distance between two views of the world by how much information it requires to distinguish them. And then we can sum over all the pairs of views. So we can take every pair of events and measure how different they are from each other.
Okay.
And then you can sum that over all the pairs. And that's the variety.
So you're telling how different two events are or two observers are?
It's a property of the whole set.
Okay.
So some cities have much more variety than other cities.
I see.
Because you need less information to distinguish the pairs of corners.
And when you say put a graph and you embed it in a space, you don't mean to say, well, let's decompose a space into simplicial.
No. I imagine that there's some way in which you can compare the view on one variety of one event with the view of another event. And I can tell you lots of ways to measure how different they are. And then I can define something like a gauge theory, where the action of the theory is to increase the total variety between all the pairs.
Oh, is this related to the Fecund universe?
No.
So
I don't know. It might be, but I don't know that it is. By the way, I never have used that term.
Okay. This is just what people describe your theory as.
This is a very important idea. This is one of the key ideas that I have a collection of 4 or 5 ideas which fit together very neatly.
Oh, I would love to explore that more.
For example, the function is closely related, it turns out, to the Bohmian potential.
The function.
There's a function on a set of triples of points which can see each other. So I can describe the universe by describing every sphere in the universe looking out. And I'm going to tell you what each event in the universe sees when it looks out. And it sees some distribution on a T-sphere.
And so why is it 3? Why not something like 2 or 4?
Because that's the way it is in 2 plus 1 dimensions.
Uh-huh. And this isn't related to the cubic, I forgot the term for it, but the cubic part that you were referencing earlier of loop quantum gravity, the cubic quality.
Oh, yes, of course it's related.
So it's directly related to the cubic, meaning the 3.
Yes.
The 3, okay.
That's another of our results.
Mm-hmm. Okay, you mentioned there are 4 or 5 results of yours that you feel like are the monumental ones that feed nicely or relate nicely to one another. Can you outline them now? Then we can explore them in detail later, but just so that we have a table of contents.
I'm going to make a causal set out of the events. And I have a universe which is constructed by taking pairs of events and joining them or not.
Okay.
And I get in that way a causal universe. I have a rule which at every moment there's a distribution of what the events at that moment see. And it's described as some distribution on the sphere.
And then you have
an action principle. The action principle depends in the normal way on a product of a kinetic energy and a potential energy. And the action can be written, in fact, as the kinetic energy minus the potential energy. Mm-hmm. And the potential energy is the variety. And the kinetic energy is basically the rate of change of the variety.
Okay.
And that, when you study it for a large set, goes over into quantum mechanics. It's non-relativistic n-body quantum mechanics.
So it's useful for me to have names for these. The first one you mentioned where there are 2 sets, is there a name for that?
I don't know.
Like you haven't coined a name for that?
No.
Okay. And then now this one about variety, does that have a name? That's the one that you developed with Barber, or inspired by Barber.
Yes, but it's a separate, it's in the context of we call it energetic causal sets.
Mm-hmm. Right. I have some questions about that.
Okay.
Which we'll get to later, hopefully. What else is there? You said there were a couple other ideas of yours that you feel like are the key ones.
So there's a relationship with game theory.
Mm-hmm.
And we've been developing it with some students.
Is this the work that is currently unpublished and you're
Yes.
still working on? Okay, that's fine.
So let me just say there's a very intriguing relationship to game theory.
Uh-huh. Okay, so there's a game theory relationship between what, loop quantum gravity in it, or the causal sets in it, or?
This current theory is describable as a game.
Okay.
So the description of the universe inside of this theory is the description of a certain kind of game.
And who would the agents in the game be? Particles?
Observers.
And they have to be rational observers, or
No,
what are
they don't have to be rational.
Uh-huh.
Because they don't have. These are games which go by the name of infinite games, and they don't have a desire to win. They have a desire. They have a mutual desire to keep the game going, which is what is called an infinite game.
And from this, you get
the dynamics that I was talking about.
Uh-huh. So in game theory, there's something called mean field game theory. Is that then supposed to be the effective field theory of this physical theory?
I know so little about game theory. It's embarrassing.
So, well, okay. What inspired you to go in this direction then?
I have no idea.
Not your collaborators. There's just this idea just slowly developed.
Yeah. I was thinking that what a cosmology has to be. And the cosmology can't be we can't try to maximize something, because that's what we would do if there was one observer.
Mm-hmm.
But we have many observers. So how do we describe a system that's trying to maximize something in the context of moves made by many observers?
In one of your books, you had posited the idea that the universe begins by varying the laws. And then there was actually a prediction from this.
Yes, and this leads to that idea.
Uh-huh. What I want to know about that idea is that when one says, look, let's take an evolutionary approach to cosmology. Let's vary the physical constants anytime that there's a new universe. Well, why are we choosing to vary the physical constants only? And from what set do we choose the distribution? And I'll give you an example as to where my question is leading. So let's say biology works with variation. Okay, so variation, but it's not like, look, let's have a plant, and then there are a couple of properties of a plant. There's the stem length, there's the leaf length or extent, and then there's how many leaves, how many stems, and so on. So let's tweak those parameters. Yes, we can tweak them all day, but you'll never get to a ladybug from that. Why do we think that if there's some evolutionary progress to the universe where something is being varied, we have to put a limit on this something? How do we know that that it's not the law of the excluded middle is now gone in this universe?
Right.
Or F equals
right.
M times V instead of M times A in this universe?
These are all important questions.
Yeah.
And we have to adjust them. We have to understand them.
Mm-hmm.
We're barely starting on this idea of an evolutionary universe.
So you're starting with the idea that, look, there's a few parameters in the standard model, I assume, or lambda CDM, and then you just vary those?
Yes.
Sorry, wait. What is what we call? You said this is what we call the
question of what do we vary?
Yes.
That's called the Mendelov dilemma.
The Mendel law.
Meta is in greater than law.
Yeah. Oh, Mendel law dilemma?
Yeah, but it's not a dilemma. We just say yes. And we just do it again and do it again, do it again. So we accept the idea that there's a Mendel law.
Okay. Interesting. Speaking of a realist notion of time, there is Tim Maudlin. There are a few physicists who are strident realists of time. So much so that they think it's the fundamental ontological entity. What is the difference between Tim Maudlin's idea of time and yours?
Well, I don't know his whole description or his whole theory. So I can't really comment completely on his. We have a definite structure, and that's a advantage and a disadvantage. And by the way, you should definitely mention my collaborators, and this is not just me.
Of course, yes.
Also is Marina Cortez, right, who's a cosmologist. There is Clavio Veres and a few other people, but those are the keys, and Roberto Unger.
What do you see the difference between physics and philosophy as being?
In the present world, or ideally?
In our present world.
I think they're trained very differently. I think philosophers are trained to make key arguments, to learn to make a powerful argument.
Uh-huh.
And physicists are trained to discover things,
Yes.
ideally.
And so, what's the difference between physics and metaphysics?
I don't know. I don't know what metaphysics is, really.
What's the difference between when you collaborate with a physicist versus a philosopher? Because you've done both.
Yes, but philosophers out of Warford are not in the mainstream of well-trained philosophers.
Oh.
I mean, Clavia will be one by the time she's done, but she's a PhD student now. She also has another life where she's a published and much admired poet.
Interesting. So there's something called the Unruh effect. So do you mind outlining what the Unruh effect is and how loop quantum gravity explains it?
I don't know that loop quantum gravity explains it. It's a very good question. But the Unruh effect says that if you take an observer, which is a constant acceleration, mu-nc in space-time, the observer will see the world around it as hot with a temperature T is h bar over 2 pi c times the acceleration.
By the way, I heard that the trio of you, Carlo Rovelli, and Abai Ashtekar, all of whom have been on the channel now, by the way, Theories of Everything, that the trio has the different advantages and disadvantages. So the advantages are Abai is much more rigorous, and Carlo is much more metaphoric and poetic, and you are the middle ground.
No, that's not how it was in the war, but okay. Abai is definitely very strong, looking for exact mathematics. So he over in the camp of the mathematical physicists, and he can prove theorems. Carlo is the hippie, happy, come into my room and learn all about time version of Carlo.
What do you mean by Peter Voigt is a mathematical mystic?
I have no idea.
So I have that as a quote, but I don't remember the source.
I don't think of him as particularly... I think he's very pragmatic. Pragmatic is the word I was looking for to describe a type of philosophy, which is not the same as American pragmatism.
Said that the many worlds interpretation is a badly thought through version of Bohm's interpretation. Can you explain?
The mathematics is the same.
Well, why is it a badly thought through version? So firstly, what is Bohm's? Many are familiar with the many worlds. Whether or not they're familiar with what many worlds actually is, that's another story. But they're unfamiliar with Bohm's. So can you please outline what Bohm's is?
Bohm's and Duality was the original interpretation of quantum mechanics. And in it, there are particles and waves, and they're both real. Remember, we're realists now, and they're both real. And there are more laws because you have the particles are real and the waves are real. And the other laws refer to the motion of the particles as a function of where the waves go. So there are additional laws that give you equations that the particles follow a certain velocity or a certain acceleration, and that with respect to the waves, and the waves follow the Schrodinger equation as before. And so you get, right, they're weird in some applications, but you get the equations of quantum mechanics. But the wave equation is the realistic equation for the waves to travel. And the particle equation is a new equation that tells you how the particles move.
So how does that have anything to do with many worlds?
You have the same problem, which is that, how can you say it? There are ghost solutions. In other words, in the many worlds, there are many solutions. There are many ways, solutions to the waves. And they don't change. They're the same equations as they were before. But you have to account for them. So in other words, every time in the many worlds interpretation, where the waves would, quote, split, and some would go this way and some would go that way, you have the waves still splitting in Bohm. But there's no particle, there's only one particle that follows them. So you've got zillions of ghost waves.
So do you have a preferred interpretation of quantum mechanics?
Yeah, mine. I think the others.
What is the name of yours?
It doesn't have a name because nobody talks about it.
Okay, what is it? Do you mind describing it?
It's a low energy limit of the causal theory of views. In the limit that you have non-relativistic particles, and there are many of them. So you get it from that as you get quantum mechanics has a description of the limit as n goes to infinity, and certain forces scale with certain powers of n.
I don't understand the interpretation. So what is it? So usually interpretations say, what is the wave function?
Yes, the wave function emerges as a description of the evolution of the probabilities. So I have to go through the stochastic. So it's a little bit stolen from the people who made the stochastic formulations of quantum mechanics.
Can you contrast that with something like the Copenhagen interpretation?
Well, there's nothing. The Copenhagen interpretation is not an interpretation of quantum mechanics. It's a perfectly good pragmatic physical theory to describe what's going on, but it's not. There's no realism at all. That is, the observers believe that sometimes they see particles and sometimes they see waves. They believe strongly there's this division of the world, just two parts. And by the way, I would say that there are two parts to the world, but I would say that one of them is the future, and the future is described by the Schrödinger equation, which only describes the future, describes how states in the future evolve backwards and meet us in the present.
Wait, how states in the future evolve backwards and meet us in the present? So like retro-causality or
yes, retro-causality. It's a little bit of it too.
A little bit of it.
Yeah. So it's sort of a mixture of retro-causality. Well, you mentioned before, I forget what you just mentioned, but it is also has this bit of retro-causality in it.
And is this related to the thick present?
Yes, of course.
So a little bit of it meaning you can't go backward in time or influence what happened 1 year ago, but you may be able to influence what happened a microsecond ago?
So what? Yes, I'm sorry.
This microsecond, I just use that as an indistinct term, but you have a number associated with it, like 300 milliseconds or half a second. Or what is that number?
I don't know. It's some.
But you mean to say that you've calculated this number, or this number must theoretically exist?
Must theoretically exist.
And there's no fuzziness even within the number itself?
I'm sure there is fuzziness.
So then does that not technically mean that you can bring this fuzziness all the way back to 1 year ago? And just with a low probability, you can influence what happened a year ago?
Maybe, yes.
Do you ever think about that?
Not enough. Yes, I think about it sometimes, but the thing is that I'm trying to do better than what I have. That is, I'm trying to do non-relativistic quantum theory. And these are really questions that will make sense. I mean, relativistic quantum theory.
Right.
And these are systems that questions that I'll be able to answer precisely when I have that.
Uh-huh.
And I have pieces of it, but I haven't worked through all the examples I want to.
And by relativistic quantum theory, do you mean QFT or something else?
I mean basically what Freddie Cajazo means when he says an amplitude, a theory of quantum amplitudes, which is relativistic.
Uh-huh.
Because I think I've fell on what Freddie and Whitten and other people have been doing for a few years. But there's some checking still to do.
What are some of the ideas in physics that you feel like, okay, firstly, there's some ideas that are overhyped.
Yeah, sure.
So what are some of the underhyped ideas?
I think the idea that there is nothing outside the universe and all the variants of that there's a finite number of particles, there's a finite number of observers, etc., are underappreciated, the power that those ideas have. I think the weak holographic principle, as opposed to the strong holographic principle, is undervalued.
What would be the difference between those two?
The strong holographic hypothesis says that to the interior, if I have a space-like sphere in 3+1 dimensions, then it has a boundary which is a space-like circle times evolution in time. And I'm sorry, space-like two-sphere.
Okay.
And the strong holographic principle says that the entropy of the system, which is defined to the interior of that S2 cross time, is limited by the usual constraint, by the entropy being in Planck units being smaller than 6 pi. And the weak holographic principle says that you should see these two surfaces as again, I'm looking for a word, but these are two surfaces that flux passes through.
Okay.
And it's a limitation on the entropy flux. And here, Carlo and Abai and I are very much in agreement. And we all have published different versions of that.
What would be a time where you, Carlo, and Abai have disagreed vehemently, maybe even an altercation, like a loud verbal disagreement, but it's led to something fruitful?
I don't think although our styles are very, very different. I mean, Carlo and I have very different views about time.
And what about Abai? Abai stays out of the philosophy?
He goes at it in a different way.
Explain to people who don't know what research is like, what it's like when you do collaboration, and what it means to have different styles. Because it sounds to most people who aren't in math or physics that it must be theorem proving. You do modus ponens, and it's logical, it's straightforward. I mean, maybe there's idea generation and then there's differences there, but how much can different styles come into play?
I don't know.
I'll give you an example. So if all you know are the rules to chess, you're just a beginner. You have no idea what it means when someone's like, Bobby Fischer was an aggressive player.
Yes.
But when you know more about chess, you see, okay, whoa, like you should be on the defensive here, but he actually takes the center. He starts attacking, he starts calling check or whatever it may be. So there's an emotional style to something that is analytical.
Mm-hmm.
Okay, and that's something that you get as you study
I
chess more.
I think people don't understand what chess or mathematics is. You ascribe much more reality to the rules of chess. I think these are all partial. I think if you play chess long enough, you discover contradictions, or you discover the inability to prove the lack of contradictions.
What do you mean by that? In chess in particular, or are you then about to make an analogy to physics?
I'm making an analogy to Gödel's second theorem.
Yeah, okay. What does that have to do with physics?
That chess is open in the same way that we were talking about games being open. That is, in chess you can have finite games, or you can have infinite games. That's why you can, what's it called? That's when you give up. I forget what it's.
Resign?
Remain first. There can be, my understanding is, tell me if I'm wrong, that there can be games of chess that can't be won by either party.
Yes, they could be stalemated.
Yeah. So chess is more interesting, I would say, as a mathematical system than most people think.
Mm-hmm. I believe it was Freeman Dyson who said that Gödel's incompleteness theorem is likely to have an implication on physics. I don't know if he said likely, but he doesn't discount it at all.
Yes, of course.
And then there's some people who say it has nothing to do with physics. It's a property of formal systems. Okay. And particular formal systems at that. What do you say?
It depends on whether you can formulate physics entirely in a correct theory, which is also finite in the sense that we were saying, in which every physics problem has an answer, which is provable or not. And I don't think we know that. I mean, I've tried to ask people and talk about it with people in mathematical logic, but I don't think there's a known answer.
You said you tried to talk about it.
Well, I have.
Yeah.
Well, because of my own ignorance.
Oh, okay. So not because they think that's a foolish idea. Why even discussing that, Lee? I'm going to go now. I'm going to have some coffee somewhere else.
No. I think there are people who enjoy discussing these things and people who don't.
Mm-hmm.
But I think that, and I could be wrong, but I think that there's a lot more openness in mathematics and chess and many things.
Mm-hmm. Then?
And once you allow that openness to come into mathematics, then mathematics becomes much more interesting because all these kinds of questions of why this and not this become more real, more present.
How do your views on biology influence your views on physics?
I think it's more the other way.
Uh-huh.
But I think that we really don't understand important things about biology. They're very basic things we don't understand. I mean, so there's this paper that Marina and her husband and Stu Kaufman wrote, actually 3 papers. And we try to discuss these questions, but they're really hard.
What are some of the fundamental questions in biology that aren't understood, or the answers aren't understood?
Well, Marina's question was, how many states are there in a biological system? And she noted that she and most people in astronomy or cosmology who had thought about it had thought that if you count up the states in the universe with using the standard model to count things and estimate the densities and so forth, you got some number and you allowed biology in, and that was only slightly more. But she claimed with Stu and not yet with me, but I think they convinced me eventually, that there are many more possible states. Yeah, I have to tell you what a state is. Mm-hmm. But there are many more possible states in a system which can include biology than in a system which doesn't. So, for example, I have to allow all those chess games that we were talking about. And I have to allow in my counting of states. So there are, let's count carbon atoms, or let's count proteins in the Earth's biosystem, ecosystem.
Okay.
Do you count the ones that are functional only, or do you count all of them? And if you count the ones that are functional, you need a language for discussing functions and counting them. And she argues that once you do that and you think about it, it's plausible that there are many more states in a system than in which, in other words, I might count, if I have a certain amount of the ingredients of proteins, and I count them as per function, I would count many more than if I just counted them as per atom. Do you see the idea?
No, I don't see why. So is the argument that, look, because you can have a thought, so you can have several thoughts, but if this were just atoms, the atoms don't have a thought. If we're to include thoughts in state space, then the entity that includes you has more in state space than if you weren't alive?
Yes.
Okay, so state space can also be understood as what potentially can exist. Potential.
Yes.
Why wouldn't that potential be there in the dead atoms versus you? That potential is there, otherwise it wouldn't have given rise to you with the thoughts, no?
Yes. But the alternative is that there's no counting of things that are different in states which this is really hard.
Oh, I'm sorry.
No. It's what we should be thinking about. This is exactly the question. Do we count? We're here on the Earth, in the Earth's biosphere. We're counting the states because we want to. And we want to know if we have a planet, that planet may in the future become alive. And it may not become alive. And my intuition, although it's taken a long time to even consider it, is that there are more states in the system which has the potential for life. And what gets me there is that I can't count functions. So let me give you an example of this. I don't see it, but somewhere in there's a hammer.
Okay.
That's a pencil. Now counting functions.
Oh, you're asking me to count its functions. Yeah. 5 functions.
Well, I certainly know there are many more than that.
Okay.
Because for every one you count, there's its function in a movie.
Uh-huh.
So there doesn't seem to be a definite number, which is the functions of that.
Professor, we were talking off air at this point about what it's like to marry someone who's not in your field. So many mathematicians or many academics marry someone in either their field or is slightly adjacent, or someone who has about their level of education. And what is it like? What are the advantages? What are the disadvantages? Or maybe you don't view it like that? What are the different styles? There's that word again.
Well, I don't know. I mean, I married somebody pretty fantastic who is trustable and beautiful and smarter than almost anybody I know. And she has had many careers. She was a lawyer. She is now a consultant. She's been an actor and a producer in theater and events. And it's wonderful. And it's very different. For example, a couple of career changes ago, she quit her job, and that made me very nervous because she made it through that job. And she said, "Trust me." And I don't know, from time to time I said, "By the way, you don't have a job. What's going on?" She said, "No, I'm doing what I should be doing. I'm lunching."
She's lunching.
She's lunching. Because she said nobody would believe that she had quit a very street firm, a Bay Street law firm, unless she did quit it. And sooner or later, she got a phone call from somebody who ran Metrolinx, and she was offered a job which didn't exist before, which was improving the communications between Metrolinx and the public.
Like a PR person?
Well, but not really a PR person. It was many aspects of it. There was PR. There was going into the community and listening. When the trucks all came down and took all the houses down.
Okay.
And she did that for a few years, and then she quit, etc. So now she works on housing sometimes. And anyway, it's interesting. But I was married before to a physicist, and she was also very interesting.
What about the non-career aspects?
Non-career aspects, like what?
So, for myself, with this job, I do plenty of thinking. Almost too much thinking.
Good. So why don't you publish it?
Well, these podcasts are published.
But...
Like publish papers?
Yes, why not?
I'm thinking about it.
Okay. Because it seems like if I'm not imposing on your structure here, it seems that most of the people you're interviewing are older career-wise than you.
Uh-huh. Explain more.
Many professional scientists and philosophers of your age or so are not doing things which are that interesting.
Uh-huh.
Which is a criticism I think they should be trying to do.
Like what? Like tackle large problems?
Yes.
Yeah, so one of my criticisms about the current academic system is that you get people when they're at their most creative, so they're 20 to 27, and then you actually tell them, they come to you bright-eyed and say, I want to solve this huge problem. They say, professor says, no. Like that, you're so naive. You'll lose that soon. What you should do is tackle a problem that you can publish on. And they'll make this huge deal about there's a difference between a problem that's grand and a problem you can make progress on.
Yes, did they really?
Yes. Then they'll say, well, look, also, if you want to get a career, you need a history and publication.
Yes.
Which means you need to specialize when you're at your most creative. So for me, what I like about this podcast is that I get to speak to so many people, and I have my own large ideas, but I also am interested in large ideas.
Right.
I get to speak to people like you, and I get an overview before I specialize.
Yes. Do you know this guy? You know this one?
Neil
Stevenson.
And Richard Powers. What are these supposed to be? What's the relevance here?
They address all the fundamental questions that you're talking about. And they don't have to answer to anybody who's capable of publications. And it has smaller data, at least as small if you don't. And the guy I've just been reading he's the best real novelist, American novelist I've read. And of course, nobody forgets his name. They just read his last book for the second time. And it's about. This is embarrassing not to remember your name. But
It's okay.
well, no, it's interesting that I don't remember his name. The book has the following. Now, here's what. If you take all the full physics and math out of the book, here's what it's about. There's a boy and a girl. They grow up separately. At some point, they're introduced to each other. And they're both brilliant beyond measure, so to speak, and insane. And it's schizophrenic. He says, and they fall in love and they don't know what to do. So that's the setting for them.
Yeah.
And there are two books, one which centers on him, sort of, and the other which centers on her. One of them dies, the other one survives. And it's a great book, I think. It's actually two books. And unfortunately, he died a few months after the paper.
Mm-hmm.
And I think that he poses the really deep questions about what is mathematics, what is physics, what is in the world, what is moved. And again, he didn't have to have any of the countless publications. He had worked for an academic institution.
He didn't work for an academic. Oh, he did.
Well, I know that they paid him, that he was at the Santa Fe Institute, where he used to have lunch and dinner with physicists. He was very shy. And so he had a version of a career. I guess now discovering that he had papers about philosophical ideas in mathematics and so forth that I'd never seen. And I can't remember his name, but it came to me.
Mm-hmm. Again, off air, I said this to you. This is a quote from my friend. He wanted to know what you thought of this. Physics does not need to obey mathematics, but our models of physics do, or tend to by design. Hence, there's a distinction between physics that we describe via models and the totally different thing, which is the physical universe.
Yes, I think that's really wise. I think that's an important distinction to start off on this thinking.
This comes from my friend Bijou. I just want to give credit right now. So can you explain why you think that's wise?
I think that let me prove to you that the model theory of science is wrong. The model theory is the theory that says that to every mathematical, how is it put, to every mathematical model, let's say, of the world, there is a version of the world.
Mm-hmm.
And in the model of the world.
That's the Tegmark one.
Yes. And you believe that there's a world that exists for every value of answers to questions about mathematical objects posed to this model world. I didn't say that very well, but I think
sure.
You mean.
Yes.
And here's a thing which is true of every version of the world I know, I can think of, which is not true in any of the models, which is that in the world, it's always some moment. It's always a moment of time. And in the model world, it's never a notion of time.
What are you most proud of?
Oh, well, I'm really proud of the quantum gravity. I think that with Carlo and Pi, we did something really nice, and it was fun. I learned through that and through other things that you can make really good friends while doing this activity of quant research, and I think that's great. I also think teaching is a great human thing, even though you have to put up with people who have bad characters, because a combination of a selfish character and what the rules of academics let you get away with can be pretty unpleasant.
What do you mean? Without giving any specific names if you don't want to, but what do you mean? Can you give an instance or speak around?
I could, but I'm not going to. Because anything I say would be misinterpreted if anybody cared. But it's also true that I am in a very different situation because everything I do is hard. So getting up in the world and getting out in the world is hard. And I used to be very lazy, and just because I could just do something, want to do something and do it.
How's that lazy?
Because it didn't require much self-evaluation or self-discipline.
Okay, you were undisciplined.
Yes. On the other hand, I'm pretty sure if I retired, I would keep doing the same stuff.
Right.
And I think that's good. Because in my story of the world, what I have to give to the understanding of these questions is not zero. It may not be enough, but it's not zero.
Suppose you were entering the field again.
Oh, I'd go into biology.
I understand. Suppose you're entering the physics field or even the mathematical field, but let's say the physics field, the high energy field, which we didn't even touch on the crisis because.
Let's talk about.
Sure. Sean Carroll has a 4-hour podcast just on why there's no crisis in physics.
I like Sean very much. I even deeply appreciate him because he learned when he first started interacting with philosophers. He wasn't very impressive, but he really studied. He really learned, and he can do the philosophical thing of make arguments on their level to them, and that's very impressive to me. And he is also a decent physicist, quite a good physicist, if I can say it. But he somehow manages to end up on the least interesting point of view on every question he deals with, and the least ambitious question. I don't know why he does that.
You mean the most conservative point of view?
Yes. And it's I don't know. Anyway, what, do you know Fire Robin?
Fire Robin?
Yeah.
Do I know Fire Robin?
Do you know of him?
No.
Oh my God. Well, that book is in my office in Waterville. Go home or just stay here and order him. His main book is called Against Method.
Against Method.
Against Method. He was a student of Popper.
Okay.
From the same sort of world of Austrian, Austrian troublemakers in the 1940s.
Yes.
And he's a great philosopher, I think. Anyway, get that book and read it. And then Farben was.
Oh, no. I know who you're referring to. Yeah, sorry. I didn't understand I thought Fire Robin was, the first name was Fire, last name Robin. No, I know who you're referring to.
Okay, good. So, Fire Robin, one of his essays, he wrote a book of essays in response to articles, critiques of his book made by more conventional philosophers. And he wrote a rebuttal to them. Anyway, he's very interesting. And unfortunately died too.
And this has to do with the crisis in physics?
Yes. Yeah. And I once asked him about the crisis in physics. So I'm really trying to lead up to that story. And he said to me, why do you care? Just do what you want to do. And nobody will stop you. As long as it's something as long as you care more than they do, that it be done, nobody will stop you. And Pice said the same thing to me. I used to have lunch with Pice, and anyway, Pice said, look, it was exactly the same in my day. They were all bastards. So I think one just tries to have courage and goes on, and that's.
What advice do you have for the teenager going into university watching this? But also, it could be the 60-year-old person who wants to re-enter the field. Maybe they've left it for a while.
I think it's about the same as it's at any age. Be sincere. If you want to be a scientist and make it worthwhile, then no lying. No
lying, you said?
Don't lie. Tell the truth. If you didn't solve the problem, then you didn't solve the problem. And you say so. My physics undergraduate teacher, Bernstein, used to tell us, if you can't solve the homework problem, then find a problem you can solve.
Yeah.
And do that and turn it in. But that doesn't work, and that doesn't make a career. At least it shouldn't make a career.
That sounds to me more like it makes a career.
Well, that's the problem. That is, aim to solve a real problem that affects our real understanding of the real world. And if you don't want to do things at that level, if you're not ambitious enough to try to do things at that level, then do something else.
Do you think there's something wrong with not having enough ambition and good about having extreme ambition?
I think we don't have enough people who have extreme ambition. No, I think it's okay that a lot of people go into university teach, because they don't have enough people doing that. But this is part of just be honest.
Mm-hmm.
And maybe your ambition is here, maybe it's here. Obviously, you would make a great teacher. And that's perfectly worth doing. And maybe you'd surprise yourself. It's really about being open to surprise.
Do you want to end the talk by talking about Parkinson's? We mentioned that off air.
Well, it's certainly true when they say it's progressive. And I think I didn't allow myself to see that at earlier stages. But I think it's all. I know I must sound like I don't know what it is, but it's a silly thing to sit in this position and say it's all about character. But in a way it is.
Why is that silly?
Because I'm losing bit by bit the opportunities to have other explanations. That is, it's not worth it to live through this if you don't find a way to enjoy it.
You mean to enjoy life or to enjoy Parkinson's? Like, what do you mean?
Well, you can. I mean both. By the way, I'm trying to solve Parkinson's.
Uh-huh.
And of course I won't succeed, but
you can make a huge dent.
Well, we'll see. I have two ideas. One of them is that the theory is chiral.
The other is the phase transition?
Yeah, but it's also chiral. It affects one side of the body before it affects the other, for a long time, only before it affects the other side of the body. And I think if you try to think about how it could be that there's something eating away at my dopamine receptors on one side.
Yes.
And just a centimeter away, there's other very similar processes going on, except they lose the dopamine. And that's very hard to understand, and that could be. And nobody's thought, very few people have thought about that.
Have you collaborated with John Baez?
No, but I'd love to. Has he thought about this?
Oh, no, not on Parkinson's. I just meant on physics or math.
I would love to. He's really interesting. Yeah, you see, if I was retired, I could just pick up and go to John if I wanted to talk to him.
Mm-hmm.
Which let me end on this story if I haven't told it to you. Do you know who BJ is?
BJ?
Working.
It doesn't come to mind.
He is a near Nobel Prize winner in particle physics.
Okay.
He invented the idea that he was one of the people who invented the idea that particle physics was about short distances where things became weakly interacting.
Okay.
So the idea of partons.
Ah.
And anyway, I met him because he got divorced, or I guess his wife died, and he got very unhappy because of that. And he works at Slack in California, but he also has a cabin way up in the hills in Wyoming or something like that he retreats to. And 1 year after his wife died, he was there in Wyoming by himself. And he read something by Carnot, and he got very interested in it and decided to rebuild the sort of loop quantum gravity as particle physics kind of idea. And anyway, what he used to do was he had an old station wagon, I think. And he loaded the back seat down with physics books that he was interested in.
Mm-hmm.
And he drove around visiting friends. And he came, this was in our first term here at Perimeter. And we had a receptionist, and she called me up one morning and said, "There's a guy who's come to see you." And I said, "Who?" And she said, "He says he's called BJ or JB or something." And he was standing in our entrance. This is the original building.
Mm-hmm.
And he hadn't told any of us that he was coming. I had maybe met him once before. But I came in, I came in as quickly as I could and started talking to him. And we invited him, of course, to stay with us. We found him a hotel because he was wanting to just camp in the parking lot.
Mm-hmm.
And he spent, in the end, most of a year with us. And that was wonderful. And that's somebody who loves physics.
The point of the story is that he just
came. He wanted to understand something. He was reading Carlo's book. And he just came.
Professor, it's an honor to speak with you. Thank you for inviting me into your home.
Thank you.
The podcast is now concluded. Thank you for watching. If you haven't subscribed or clicked that like button, now would be a great time to do so, as each subscribe and like helps YouTube push this content to more people. You should also know that there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate toes, disagree respectfully about theories, and build as a community our own toes. Links to both are in the description. Also, I recently found out that external links count plenty toward the algorithm, which means that when you share on Twitter, on Facebook, on Reddit, etc., it shows YouTube that people are talking about this outside of YouTube, which in turn greatly aids the distribution on YouTube as well. Last but not least, you should know that this podcast is on iTunes, it's on Spotify, it's on every one of the audio platforms. Just type in Theories of Everything and you'll find it. Often I gain from rewatching lectures and podcasts, and I read that in the comments, hey, Toe listeners also gain from replaying. So how about instead re-listening on those platforms? iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. If you'd like to support more conversations like this, then do consider visiting patreon.com/KurtJaimungal and donating with whatever you like. Again, it's support from the sponsors and you that allow me to work on Toe full-time. You get early access to ad-free audio episodes there as well. For instance, this episode was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough.